Welcome back to another AP Physics 1 topic overview. Today we're going to be talking about collisions for conservation of momentum. So let's get straight into our facts. So as always with these facts and the examples, they're going to be in the description down below as Google Docs. So starting off with just momentum as it is, momentum is equal to mass times velocity, so I must have movement in order to have momentum for an object, and the equation is P equals mv. My standard units for momentum, newtons times seconds, abbreviated as n times s. You can also have kilograms times meters per second. That's the same exact thing as newtons times seconds. And the direction of an object's momentum is always the same as its direction of motion. So looking at conservation of momentum in collisions. The total momentum of two objects before a collision is equal to the object's total momentum after the collision. That's objects plural. So both objects before a collision, their momentum is equal to their momentum after the collision, and we'll see that in our examples. Momentum is a vector. That means total momentum of two objects moving in the same direction will add together. Objects moving in opposite directions will subtract. Those are really important ones for today when we set up our equations. No external forces means the momentum will not change for the system. And then the last one there, system center of mass obey Newton's second law. That means the velocity of center of mass will only change when there's an external net force acting on the system. So let's now get into our example. All right, so our first example here, we're going to have block 1, or it's a ball 1 here in my simulation, of mass 0.5 kilograms. You have block 2 that has a mass of 1.5 kilograms. Block 1 is going to travel with a speed of 2 meters per second towards block 2, which is at rest. They're going to collide but not stick together, and block 1 is going to rebound off block 2 with a speed of 1 meter per second. So you can see that in the GIF down below. You have ball 1, which is the teal ball, going towards ball 2, which is at rest, or block 2, which is at rest. The first block is going to bounce off the second one. They're going to go in opposite directions. So keep this in mind. Go back to this. I'm going to have it in the chapters in the timeline of the video. Go back to this and look at this when creating the equations for momentum here. So let's go into the first part of our example. All right, so the first part, we're going to calculate total momentum of both blocks before the collision. So in order to do this, I'm going to start off with P before. My momentum before the collision is going to be equal to my momentum of both objects individually because I have two separate objects. So with this, I'm going to start off with this equation here. P before equals P1 before, which is the momentum of block 1, plus the momentum of block 2. One problem here though, block 2 is at rest. So that means it has no momentum. You need to have some movement in order to have momentum. So then I'm going to bring about here that my momentum before the collision is equal to the momentum of object 1 before plus 0 because there is no momentum for object 2. So now we're going to do our equation for momentum. So P before is going to equal the momentum of block 1. We know the equation for momentum is going to be P equals mv. So I'm going to plug in my mass for, or have the mass of block 1 times the velocity of block 1 before the collision. So that's going to be what my equation is going to look like. Now I'm just going to plug in my numbers. My mass for block 1 was 0.5 kilograms, and the speed for block 1 as it travels towards block 2 was 2 meters per second. I'm going to plug those in. Give yourself a second to plug that into the calculator, but it's just 0.5 times 2. So I'm going to end up with a momentum of 1 newtons times seconds. Or again, if you just want to have it in the SI units, you can leave it as 1.0 kilograms times meters per second. That is also correct. So let's move into part B here. All right, so looking at part B, is the total momentum of the two blocks after the collision A greater than the answer in part A, B less than the answer in part A, or C equal to the answer in part A. This is where you're going to want to look at the fact sheet, which is in the description down below, and look for a fact that is going to help us get our answer. Again, when we make justification questions like this, we want to go over concepts, we do ERC in order to justify our answers. So we're going to start off with a fact of physics. The fact here that should help us from the fact sheet is under conservation of momentum in collisions is the first one there. So the total momentum of two objects before a collision is equal to the objects, again that's plural, total momentum after the collision. So that's going to be our evidence or our fact of physics. Then our reason is going to be, since this is happening in this situation, we know from part A that the momentum of the system was 1 newtons times seconds. So I'm going to end up having here that since the two objects' momentum is going to be 1 newton times seconds, so since the total momentum of the two objects before the collision is 1 newton times seconds, I'm then going to have my claim that my momentum after the collision should also be the same thing. That's going to be essentially my answer here. My claim is the total momentum of the two objects after the collision will also be 1 newton times seconds. So answer choice C here is going to be my answer. It's going to be equal to the answer in part A. So let's now move into part C of this example. All right, so part C of the example. Calculate the total momentum of block 1 after the collision. So we're just looking at block 1 now, not worrying about block 2 at all. It just explicitly is telling us to look at block 1 again. So with this, I have the mass again of block 1. I know what that is. And I just want to look at the speed of block 1 after the collision. It tells me that's 1 meter per second. So now I'm just going to set up my equation for this. I'm going to start off with here that momentum of block 1 after the collision is going to be the mass of block 1 times the velocity of block 1 after the collision. Again, I just have m1 because that doesn't change for either situation. Then I'm going to plug in my numbers here. I have here the mass is still 0.5 kilograms, and my speed after the collision is 1 meter per second. I'm going to multiply those together, end up with my answer here, and that answer is going to be 0.5 newtons times seconds. Or again, you can have kilograms times meters per second. It's going to be the same exact thing. All right, so let's move into part D of this example. All right, so looking at part D, we're going to calculate the momentum of block 2 after the collision. So right now what we found so far, just to remind you, we found the momentum of the system before the collision. We found the momentum of block 1 after the collision. So what we have here right now, we're just going to start off with, since I'm trying to find momentum is equal to before the collision as well as after the collision, I'm just going to start off with that equation as P before equals P after. For my Regents students who may be watching this, this is actually on your reference table for AP. This is something you just have to remember. So momentum before a collision is equal to momentum after a collision. So now I just kind of want to know what the momentum after the collision is going to be made up of. So after the collision, these objects don't stick together. So that means I have two separate objects. So I have two separate momentums. All right. But I want to know if I'm going to add these momentums together or subtract these momentums. All right. So since block 1 or ball 1 is going to bounce off of block 2, that means that they're going to go in opposite directions after a collision. We saw this in the Gif earlier. So we're actually going to subtract the momentum of block 2 minus block 1. The reason why I'm going to do block 1 second here is because it is going off in, let's say, a negative direction. Because we started off with a positive P1 for the beforehand. So since it's bouncing off in the opposite direction, I'm just going to make that negative. Doesn't really matter as long as you subtract the two at the end of the day. So we have here that my momentum after the collision is momentum of block 2 minus the momentum of block 1. So now I'm going to have that P before is equal to this because now I know that P before equals P after as from earlier. And then we're going to start plugging things in. So we know, or we're going to start to do the algebra here. So we know what P before is. We know what P1 after is. We just found that in the previous part of the example. So I'm going to do the algebra here, and since it's being subtracted from P2 after, I'm going to add my momentum for block 1 to the other side of the equation. And I should have the momentum before for everything, the entire system, plus the momentum of block 1 after the collision is now equal to the momentum of block 2 after the collision. So now I'm going to plug in my numbers here, and I should end up with my answer. I know the momentum for the entire system before the collision was 1.0 newtons times seconds. I know momentum for block 1 after the collision is going to be 0.5 newtons times seconds. I'm going to add those together. That's going to be the momentum of block 2 after the collision. As you can see here, highlighted in the white box, 1.5 newtons times seconds is going to be the momentum of block 2 after the collision. Now I'm going to use this momentum for block 2 in order to get its speed after the collision. So that's going to be the last part of this. Then we're going to test it to make sure that physics works. So let's get into the last part of our calculation. All right, so looking at part E, we're going to calculate the speed of block 2 after the collision. So again, we just found in the previous part the momentum of block 2 after the collision. We also know its mass, and we're trying to find the speed v of this block. We know momentum P equals mv. Since we have the momentum of block 2 after the collision, we can set that equal to my mass of block 2 times the speed of this block after the collision. And that's going to be shown here as momentum of block 2 after the collision is equal to the mass of block 2 times the velocity or speed of block 2 after the collision. Now I want this speed by itself on one side of the equation is attached to m2 by multiplication. So I'm going to do the opposite of multiplication and divide out m2 on both sides of the equation. So I'm going to end up with the momentum of block 2 after the collision over the mass of block 2 is equal to my speed of the block after the collision. Now I'm going to plug in my numbers. I know the momentum of block 2 after the collision was 1.5 newton times seconds over the mass, which was 1.5 kilograms. I'm going to plug this in, and 1.5 newton times seconds over 1.5 kilograms. 1.5 over 1.5 is going to give me 1, and those units end up becoming meters per second. So that's going to end up being my answer here for my speed after the collision. And again, with these numbers, it's not just enough to get the numbers. We're going to go ahead and test this on the next slide. I have the simulation from FET Sims, and I'm going to have that in the description down below, or as a pinned comment down below as well. So let's move into our actual test of this. So as you can see here, I have my simulation as a GIF. I have block 1 going towards it initially at a speed of 2 meters per second. When they collide, they both go off in opposite directions at 1 meter per second. As you can see, changing here on the bottom, let me just circle this so it's a little bit more clear. You see your velocity here. Looking at the changes there after the collision, and you can see that for 2, it's going to change to 1 meter per second as well. So we can see that physics does indeed work for this momentum equation here in this conservation of momentum. So let's move into our second example here. All right, so looking at example number 2, we have block 1, which has a mass of 3 kilograms. Block 2 has a mass of 1 kilogram. Assume block 1 moves at a speed of 1 meter per second towards block 2, which is at rest. Blocks then are going to collide and stick together. As we see here in the GIF down below, we have ball 1 or block 1. It's going to move towards block 2, and they're going to end up sticking together and moving together as one object here to the right. So now let's move into the actual math part of this example in order to make our predictions. Alright, so now looking at part A, I'm going to calculate the total momentum of the 2 blocks before the collision. So before a collision, again, we're going to have 2 separate objects. So technically, we have 2 separate momentums, even though at this moment, block 2 is at rest. So we pretty much know what that means for the momentum of that object. So we're going to start this off again with the equation of the momentum before is going to be equal to the momentum of block 1 before the collision plus the momentum of block 2 before the collision. We do know again that we must have movement in order to have momentum. We must have that velocity. Block 2 is at rest, so it has no momentum. So we have here again, the momentum before the collision is equal to the momentum of just P1 plus 0 for the momentum of object 2 here. So then we're going to set up our equation for momentum of object 1 or block 1, and that is the mass of block 1, so that's m1 times the velocity of m1 before the collision, which was 1 meter per second. So we're going to have here momentum before is equal to the mass m1 times the velocity of block 1 before the collision. Now I'm going to plug in my numbers. should have here 3 kilograms times 1 meter per second. Plugging that into your calculator, 3 times 1 is obviously going to be 3, having the proper units of newtons times seconds, or you can keep it as kilograms times meters per second, whichever one you prefer. That's going to be my answer, 3.0 newtons times seconds. So let's move into part B. All right, so part B is the total momentum of the two blocks after the collision greater than the answer in part A, less than the answer in part A, or equal to the answer in part A. This is very similar to example number 1. So same exact idea. You go look for a fact of physics on your fact sheet. That's going to be your evidence. Your reasoning is going to be whatever happened in the situation, then make your claim based on that. So again, my fact of physics I'm going to end up using here is the first one under conservation of momentum in collisions. And you have the total momentum of two objects before a collision is equal to the objects, plural, total momentum after the collision. That is my evidence or my fact of physics. Then I'm going to have my reasoning based on this. I'm going to say that since the momentum of the two objects before the collision, or the total momentum, was 3 newtons times seconds, that's going to be my reason. I'm then going to make my claim that the total momentum of the two objects after the collision should be the same value, which should also be 3 newtons times seconds, which is my claim that the total momentum of the two objects after the collision will also be 3 newtons times seconds, or 3 kilograms times meters per second. So again, my answer here is going to be answer choice C, equal to the answer in part A, which again was 3 newtons times seconds. So let's move into part C of this example. Let's take a look at part C. We're going to calculate the speed of the combined blocks after the collision. So after the collision, we know that they essentially become one object. Again, with this, since we're looking at before and after the collision, I'm going to start off here with my momentum before is going to be equal to my momentum after. Now, what exactly is the momentum after the collision? We have two blocks, they essentially become one. But right now, just kind of going off our facts, we know they move as one object, but they're going to move in the same direction. So my momentum after the collision is going to be the addition of momentum of block 1 and the momentum of block 2. Again, they're moving in the same direction, so we add these together. Then we're going to have our equation for momentum for each object. So momentum of block 1 is going to be the mass of block 1 and the velocity after collision. Same thing for now block 2, but it's just going to be the mass of block 2 times the velocity after the collision. Since they move as one object, they must move here at the same exact speed. So I'm going to have both them as velocity after and not like v1 after, v2 after. As you can see here again, mass 1 times velocity after plus mass 2 times velocity after. Again, they move as one object, so they have the same exact speed after the collision. This allows me then to factor out v after and then have here my momentum after collision as the mass of block 1 plus the mass of block 2 times the velocity of both objects here together. Now I know that my momentum after the collision is equal to momentum before, so I can do here as momentum before is equal to the same thing I have, m1 plus m2 times the velocity of the combined blocks after the collision. Now I'm going to do a little bit of algebra to get that velocity after the collision on one side of the equation by itself is multiplied by m1 plus m2. So in order to do the get this by itself, I do the opposite operation, opposite of multiplication, divide out m1 plus m2. So I should end up with my momentum before the collision over m1 plus m2. That's equal to my velocity after. Now I'm going to plug in my numbers here. Remember, my momentum before the collision was 3 newtons times seconds, and both my masses here are above 3 kilograms and 1 kilogram. That's equal to my velocity after. Essentially, that leaves me with 3 newtons times seconds over 4 kilograms. If you plug in 3 over 4 into your calculator, you're going to end up with 0.75 meters per second as my velocity after the collision. Again, we're going to go ahead and test this on the next slide. in my simulation. I made a GIF of that again in order to make sure that physics does work, but you should end up getting 0.75 meters per second. So again here, look at my velocity here on the very bottom. I'm going to circle this once more. This is a simulation from PhET. So I'm going to have this in the description down below or pinned as a comment so you can test this out yourself. But when you do, again, when you actually do this, you want to make it fully inelastic so they don't bounce off each other. But if you do indeed do this, you're going to get that the velocity of both objects as they move as one are going to be 0.75 meters per second. So we showed here that physics does indeed work, and we can use math to make predictions in real life situations. So I hope these examples were helpful, and see you guys in class.